know the sound. An ambulance races down the street toward you, the siren blaring at a high wail, and then, the moment it passes, the sound instantly drops to a much deeper drone. That shift in sound is called the Doppler effect. To understand exactly why it happens, we are going to look at how a sound wave's frequency relates to pitch, what physically happens to sound when a source is moving toward you, and what happens when it moves away. Let's look at this split-screen visualization. Before we add motion into the mix, we have to define exactly what frequency is. Frequency is simply the number of complete wave cycles or patterns that occur each second. We measure this in a unit called hertz. The vibration of a source, like a guitar string or a siren, determines that frequency, and we experience it as pitch. On the left, a sound wave with a high frequency sounds squeaky or high-pitched. On the right, a sound wave with a low frequency is what we call deep or low-pitched. So, if a source is standing perfectly still, the physical spacing of the wave it creates directly dictates the pitch that reaches your ear. Here is an animated model showing our ambulance with its siren on. It's moving directly toward a stationary observer. As the vehicle moves forward, it is chasing the very sound waves it's emitting. This forward motion causes those expanding circles of sound to physically bunch up in front of the ambulance. Scientifically, because those waves are compressed together in the space ahead of the vehicle, the observed wavelength of the sound is becoming lower. The physical distance between each wave crest is shortened. Because these waves are packed so tightly together, more of them strike the stationary observer's ear every single second. A higher number of waves hitting your ear per second means the observed frequency is higher. The forward motion of the vehicle creates a physical compression of the waves. This tricks the observer's ear into hearing a higher pitch than the siren is actually producing at the source. Pause right here. The ambulance has just passed the observer. Based on what happened in front of the vehicle, what do you think is happening to the sound waves trailing behind it? Let's watch. As the source continues driving away, it is physically pulling away from the sound it just emitted. This motion drags the wave pattern, causing the trailing circles to stretch out. Because the space between each crest is expanded by the vehicle's departure, the observed wavelength is becoming higher, meaning it is physically longer. With the waves spread far apart, fewer waves reach the observer's ear each second. Because there are fewer cycles hitting the ear per second, the observed frequency is lower. The stretching of those trailing waves results in a drop in frequency, and your ear processes that lower frequency as a sudden shift to a deeper, lower pitch. Let's summarize this sequence with a table. When a sound source is approaching, the wavelength decreases, the observed frequency increases, and the pitch you hear is higher. Conversely, when the source is moving away, the wavelength increases, the observed frequency decreases, and the pitch you hear is lower. And there is one final rule to remember about velocity. The faster the source is moving, the more it compresses or stretches those waves, resulting in a bigger change in frequency and wavelength. Let's do a quick check of what we've covered. First, what is the unit of measurement we use for the frequency of a wave? It's hertz. Next, how does the human ear interpret a low-frequency sound wave? We hear it as a deep or low pitch. Finally, what happens to the physical wavelength of a sound when an ambulance is driving away from you? The wavelength gets longer or higher. The Doppler effect is simply the physics of motion altering the geometry of waves before they reach us. If you can visualize the vehicle bunching up the waves in front and stretching them out behind, you'll always be able to predict the pitch.